Many of you have told me that you're facing problem with indefinite integrals. So I'm trying to, broadly categorize the entire thing into some special categories so that you can identify the sums. So basically, indefinite integrals can be broadly categorized into three different methods. One is substitution, then you have partial fraction, and then by parts. So I believe, based on your inputs, that this is the portion that is creating the most of the problem. Before starting with substitution, let me just tell you one thing, that yes, substitution, there are a vast variety of sums on substitution, so you really, really need to practice. But partial fraction and by parts, these two have a common, specific, not common, specific algorithm or structure, and you are almost, it is almost 100% sure that you will get sums from these two portions, partial fraction and by parts. So make sure that you prepare the partial fraction and by parts very, very thoroughly. And then substitution, if you can uh, practice enough, of course you can do. So I'm going to deal with this part, substitution part. Now, instead of going into individual sums, what I will try to do is first, give you various categories of sums which you can deal by the substitution method. So the first category is I'm going to deal with trigonometric functions. Okay. So if you have sums like sine cube x dx, or say cos cube x dx, that is either only sine or only cos with a cube. So in this case, use the formula sine 3x equal to 3 sine x minus 4 sine cube x, or cos 3x equal to 4 cos cube x minus 3 cos x. Use these two formula to transfer the integral from cube to multiple angles form, and then you can easily do the integration. Second is, suppose you have sine 4x dx or cos 4x dx. In such case, you will use the formula, the multiple angle formula that you have, in fact the sub multiple angle formula, that is 1 plus cos 2x equal to 2, or rather let me use the sub multiple form, 1 plus cos x equal to, no, sorry, it is 2x, 1 plus cos 2x equal to 2 cos square x, and 1 minus cos 2x equal to 2 sine square x. So from here, uh, you will replace the this one, you have to write it as sine square x into uh, sine square x whole square, and then sine square x is 1 minus cos 2x by 2, whole square. Now if you break the square, then it becomes easily integrable. Similarly here, you will do cos square x whole square, and then cos square x is 1 plus cos 2x by 2 whole square. Again, break the formula, and then you can easily integrate it. So this is the second type that you have. Next, suppose you have uh, say you have sine square x. So till now we were having only sine or only cos. So now suppose you have a mixture of sine and cos like this. Of course, you know that you will, for this you will have to use the formula that sine 2x equal to 2 sine x cos x, because this can be written as 1/4 2 sine x cos x whole square. And then you know what to do. You can easily integrate it. So this becomes 1/4 sine square 2x sine square 2x dx. Then go back to the previous type, that is you replace sine square by 1 minus cos 4x by 2 dx. That is this one, this thing. You are using this same technique here, where you are replacing sine square x by this formula. So this is third type. Fourth is if you have a mixture of sine and cos but with a cube. Sine cube x cos cube x dx. So here we apply the same manipulation as we did in the previous case, because you have sine cube, but the only thing is the adjusting factor will become then 1 by 8. So this will then become sine cube 2x by the same formula, that is this formula, this formula. And then again same method, 1 by 8. Now since this is cube, so we will use the first form. Remember this one, sine cube. So we will use this formula and replace the cube by multiple angle. So this becomes 3 sine 2x minus sine 6x by 4 dx. Then you can be easily integrated. Now suppose you have sine 4x cos 4x dx. Again same method, this time it will be 1 by 16 sine 4 2x dx. So 1 by 16. So when you have cube, you use the cube formula. Whenever you have square or 4 power, then again you use the same, that multiple angle formula. So this one becomes 1 minus cos 4x by 2 whole square dx. Basically you write it as, this portion you write it as sine square 2x whole square, and then you replace sine square 2x by the above multiple angle formula. So these are the some of the few very common trigonometric functions that you get. Uh, Now you could wonder that what happens if I get sine 6x cos 6x. So I've done only 2 and 4. What about 6, 8? No, those sums cannot be easily done by this method. It will be very lengthy. Those are tackled by something called by a different method, which is not under class 12 syllabus. So I don't think you will get power greater than 4. Okay. Now, so uh, these types that I had discussed till now, uh, more or less, I have taken individual sums, though I have not solved them, just to give you the different types. Now, what I'm going to discuss is completely a general discussion on trigonometric functions. So, this is, you could say, generalization. This is generalization of the various types of trigonometric functions that you get in the indefinite integrals. So, first is your integral is of the form sine mx cos nx dx. So now this is the form that you have sine mx cos mx, where mn can be any value. I mean any value here, I mean they are natural numbers. They can be odd or even. M and n are natural numbers, they can be odd or even. Now, if you have m odd, then notice that I'm not looking at n at all. M is odd. Then you put cos x equal to t. If you have n odd, then you put sin x equal to t. So let us see examples on these two first. For example, if you have sine cube x cos 4x dx. So here you can see that if I consider m as the power of sine, then m is odd. So we will put cos x equal to t. So obviously sin x dx equal to minus dt. So ultimately what will happen? This integral, you look at the integral like this, sine square, because you need one sine x with dx, so break the sine cube into sine square x, and then uh, cos 4x, you can write it as cos, okay, so cos x is t, so no problem, cos 4x, and 1 sin x dx here. So now when you substitute, what do you get? Sin square x is 1 minus cos square x, so 1 minus t square. Cos 4x is t4. Uh, Sin square x, cos square x is this 1 minus t square t4. Yes, sin x dx is dt. Now this is easily integrable. Okay, so here we did an example where m odd. Now let us take another example. Say sin square x cos 5x dx. So here you have n odd. N odd. Okay. So here we will put sin x equal to t. So I'm not going into the details. You can do the detailing part. So break this as sine square x cos square x whole square and then 1 cos x with dx. So when you use this substitution, you end up with the expression integration t square 1 minus t square whole square dt. So that is a polynomial in t and that can be easily integrated. So I showed two examples of the type this m odd cos xt, n odd, then sin xt. Now, what is the third? Third is if you have m and n both even, m and n both even. So m, n both even. Remember, we have already done some sums just previous to this section where m and n were both even. Here we have done here, see, m and both even. One is 2, one is 4. But the difference here is we have taken the same power here, that is 2, 2 or 4, 4. Now, if m and n are both even, then normally what we do is very broadly speaking, extract sine square x, cos square x. First of all, do this. Then use the multiple angles formula for sine 2x or cos 2x. Okay, so now let's take an example. Say you have sine square x, sine 4x and cos square x dx. So, as I told you earlier, in the previous two examples also we have taken m and even, but there m and n were equal, but you might not always have equal. So, this is one such sum where m and n are even, but they are different. M is 4 and n is 2. So, as I said, try to extract the sine square x's and the cos square x's from this. So, first we will manipulate the integral like this. From sine 4x, I take sine square x, pair it up with cos square x, and leave one sine square x outside. As soon as you do this, this portion reduces to the first type that we have done. That means if you manipulate it, then this will become sine square 2x. And this sine square x remains as it is. Now use the multiple angle formula that you have. So sine 2x, sine square 2x is 1 minus cos 4x by 2. And sine square x is 1 minus cos 2x by 2. So you get the idea what to do. So this is how you tackle when both the powers are even but not equal. Right. Now there is another type. Till now we have been dealing with powers m and n, just natural numbers. Now this is a very special type that we are going to discuss now. Here m and n, they belong to Q, that is they are rational numbers such that very special type of sum. That why I'm saying, because they are not just any two rational numbers, but their sum, that is m plus n, is negative. So this is the condition under which we can apply this method. I'll do an example, then it will become clearer. So what are the steps we are going to do? So first, you see, uh, you know that m plus n is negative. So first step, divide numerator and denominator by cos to the power minus m plus n x. This is the first step. Then the second step, put tan x equal to t. Okay, so these are the two main things that we are going to do. Now let us take an example, then it will become clearer. Okay, suppose you have integration dx by root over sine cube x cos 5x dx. The sum apparently looks terrible, right? How to break it and all that. But let's check what are the m and n's. Now, if you look at the sum, then your this integration is like this. If you take sine and cos to the numerator, because remember, when our form of the sum is integration sine mx cos nx dx, where mn belong to q and m plus n negative. So these m's and n's are, we get the values of m and n's only when the sine and cos are in the numerator, but here they are in the denominator. So we convert them to the, rather transfer them to the numerator and then check their powers. So if you take this to the uh, numerator, then what do we get? So we can write it like this, right? This is just I want to show you, but we are not going to use this in the original process. So this can be written as sine to the power minus 3 by 2x cos to the power minus 5 by 2 x dx. So this is how I can express this integral when I take sine and cos to the numerator. So my m and n will be, therefore, my m is minus 3 by 2 and n is minus 5 by 2. So therefore, what is m plus n? Your m plus n is minus 4. Right? Okay. So that means this sum satisfies the criteria that we need for this process. Now let us come back to the process. So once we check that this is happening, then the next step that we are going to do is we are going to divide. Remember, the first step is divide the numerator and denominator. So let me write it here. We are going to divide numerator and denominator by cos to the power minus m plus n. So that is plus 4x. So we are going to divide that. So let me show you here separately that if I divide, so now my integration is this. Suppose this is the integration, the blue one. I've rewritten the integral. So now if I divide it by, uh, so let me erase this portion and delete with this blue color. Okay. Uh, okay, fine. Oh no, that will be, no, we are going to, sorry, sorry, we are going to deal with this portion, the original portion. So if I divide, numerator is just 1. If I divide it with cos 4x, then this becomes sec 4x. Okay. Now let us see what happens to the denominator. That only the denominator part. Now the denominator is, I'm showing it here. The denominator is sine to the power 3 by 2x into cos to the power 5 by 2x. So only the denominator, because when I divide the denominator looks quite complicated with the roots and the 3's and the 5's. So I'm showing this part of the calculation separately, that when I divide the denominator by cos 4x, then what form does it take? That is why, that's what I'm showing. Now if you simplify this, then this becomes sine to the power 3 by 2x, and this is, if you laws of indices, I'm simply applying laws of indices. So this becomes cos 3 by 2x. That means it becomes tan to the power 3 by 2x. So this is what we are going to directly write here. So it becomes tan 3 by 2x. So you can you can also, in the exam also, you can show this calculation part of the denominator separately. No problem with that. Now, once you are done, you have attained this portion, then it becomes very easy. Whenever you have sec 4x, I think you already know that you separate it into sec square x and sec square x. And for 1 sec square x, you write 1 plus tan square x whole divided by tan to the power 3 by 2x. So now if you put tan x equal to t, that was the second step for dealing this type of sum, then this converts to the form 1 plus t square by t to the power 3 by 2 dt, which can be easily integrated. So these are the few types of special types of trigonometric sums that I wanted to discuss. Now we will pass on to the next steps. Okay, so now I'm going to give you some sums for you to practice based on the above categories that I just discussed. So let me just give you the sums along with the answers. The expressions in the third bracket will be the answers. Okay. Now, a few other types of sums that involve tan and cot. Okay. So the first type is uh, if powers of tan or cot are odd, then what you do is you extract tan x sec x or cot x cosec x from the given integral. Then you substitute sec x equal to t. Let's take examples. Say example 1. Say you have tan cube 2x sec 2x dx. So here you can see that power of tan is odd. So obviously we will break up this power, that is cube, into one is tan square 2x and the other tan 2x we pair up with sec 2x, that is we are extracting tan x sec x, and then you put sec 2x equal to t. So then this integration reduces to simply polynomial integral, that is t square minus 1 dt. Example 2, suppose you have cot cube x dx. So here power of cot, instead of tan you have power of cot odd. So I have to extract cot x cosec x. So obviously what we do is we split it up, the cube we split it up like this, cot square x into cot x dx, and then cot square x is cosec square x minus 1 cot x dx. So ultimately you have cot x cosec square x dx minus integration cot x dx. The second part you have direct formula, direct special formula you have. So now you put, just as here we put sec 2x equal to 2, here we put cot x, sec 2x equal to t, sorry, cot x equal to t. So the this equation then reduces to just simply minus t dt minus cot x dx. So this substitution is for this part. So let me add here, put sec x equal to t or cot x equal to t, depending on whether you have tan x or cot x in the sum. So this is when you have the powers of either tan or cot odd. Next is if powers of tan or cot are even. So powers of tan or cot even. So what do we do? In this case, extract tan x sec x. If it is even, then you extract tan square x and sec square x. Then you put tan x equal to t, or extract, if the sum is in terms of cot, then you extract cot square x and cosec square x, and then put cot x equal to t. So this is a general method. Now let's take up in individual sums. Say example 1. So we need even powers. Say you have tan 4x dx. So if you have even powers, we have to extract tan square x and sec square x. So obviously what we'll do is 1 tan square x, and for the other tan square x we write sec square x minus 1 dx. And then you put tan x equal to t. Example 2, if you have cot 4x dx, then similar treatment, 1 cot square x, and for the other you have cosec square x minus 1 dx, and then put cot x equal to t. After this you can easily manage. Okay. Suppose you have a sum like this. Example 3, where you have, say, tan 8x and sec 4x dx. So here again we are dealing with even power of 10. That is the first case. So we have to extract, somehow we have to extract tan square x and sec square x. So we just rewrite it like this. Uh, tan 8x, and then sec square x is split into sec 4x is split into sec square x into another, for another sec square x we write 1 plus tan square x dx. So now if I put tan x equal to t, then this becomes manageable, because sec square x dx, that is this portion, will become dt 1 plus t square t to the power 8. So this becomes t to the power 8. This portion becomes 1 plus t square, and the rest of the portion, that is sec square x dx, becomes dt. So you can manage it. So moral is, this is how you manage your integrals if they contain tan and sec, tan, sec or cot cosec. Right. Now, uh, I'm going to deal with a different category of sums now. Uh, Let me name it type D. Type D. Now, under this type, there is a what to say, and there's a specific pattern of the sum. So it is difficult to put them into words, so I'm going to write them in terms of symbols. So the first type is if you have an integral of the form sine x by sine x minus a, where a is a constant, simply a constant. So if you have this, then just do this simple manipulation. That is, since you have x minus a in the denominator, so here you write x minus a plus a by sine x minus a dx. And then you treat this, you have to apply compound formula, treat this as a unit and this as a unit, and then apply compound formula for sine. So that is sine a plus b. So sine a cos b plus cos a sin b by sine x minus a dx. So now if you split it from this sign, so obviously you are left with cos a dx plus sin a cot x minus a, for which you have direct formula. So the sum has been tackled. So this is one pattern. Now suppose you have sin x plus a. Instead of sin x, you have sin x plus a, and you have sin x plus b. So what is the manipulation here? See, for the previous sum, the most important step is this portion, this manipulation. That helps you to get to the end. Now, in this case, what we'll do is, since there is an x plus b in the denominator, so the manipulation is simply, I will bring one x plus b, and then this b is not there in the numerator, so we'll remove b, but a is there, so a minus b. So a was a x and a, they were already there. I introduce a plus b and remove it by minus b. So this is the manipulation that I do by sine x plus b. And then again, sine a plus b formula, if you split along this plus sign, you can manage it. So I'm not completing it. I've shown it in the first sum. So after that, you can do it on your own. Next, type 3. That is, you have only dx in the numerator, and in the denominator you have both sine both the expressions are with sine x minus a, sine x minus b. So now what is the manipulation here? What we are going to do is, since you have sine x minus a and sine x minus b in the denominator, we are going to do this manipulation. Sine, first I bring x minus a, and then remember there is nothing in the numerator, only 1. So whatever I introduce, I have to get rid of also. Now sine x minus a, and you also need one x minus b. So x minus b you need. Now if you put a plus here, then it becomes twice x. It is difficult to manipulate variable, but it is very easy to manipulate constants. So instead of plus, if I put minus, then what happens is this plus x minus x get cancelled. So I don't have to worry about the variable. And the constant is very easy to manipulate, because now if you see what is remaining, plus x minus x cancel, you are left with minus a plus b. Sine b minus a you are left with, right? So we will just adjust that. So sine b minus a, just to adjust it. So now you have only 1 in the numerator. And then denominator, original denominator, whatever you had, you preserve it. X minus a sine x minus b. So this is the main part, this manipulation. This is the main part. So this portion is a constant, so it will come out. And then if this comes out, then you apply sine a minus b compound formula, and the sum gets done very easily. Okay. In the previous sum, let me just highlight the manipulation. This is the manipulation that we have done. Now the fourth type is similar to third type. The difference being, instead of having two sines, you may have two cos. But the method is same. Cos x plus a, cos x plus b dx. So again, we do a similar type of manipulation. The only difference is, in the last sum you had sine in the denominator and you used sine in the numerator. Now here I am using, though there are causes here, I am using sine here. Sine. See, integration, it is not that you have to do by this method only. You may do by other methods, but I'm just showing you that this can be done by this method also. Okay, so you have x, instead of x minus a, you have x plus a. Now, instead of x minus b, you have x plus b. So that is what we need. So we will need one x plus a. We will need one x plus b. But again, by same reason, I cannot put plus, so I will put minus. Now what happens? We have in the numerator introduced a new term, which is sine a minus b. Sine a minus b, which was not there. So I adjust that. Sine a minus b. And of course, this part is constant and will come out of the integration. And the original denominator remains x plus a cos x plus b dx. And then after this, you split here, applying sine a minus b formula. So this is the manipulation. So these are the four types I wanted to show. You will find a lot of sums in your books of these categories, so you can practice one or two of each type. So I'm mainly discussing the categories. Now there is one important sum which I want to discuss. Let me name it, say, an individual category, say E. Okay. The sum is integration sin x by 1 plus sin x dx. Now, I think the easiest way of doing this sum is, sometimes you multiply with 1 minus sin x up and down. But I think the best way to do this is, since you have a sin x plus 1 in the denominator, you introduce 1 plus 1 and then remove it by in the numerator, and then so this is a very simple manipulation. And then you split it up from here, sin x plus 1 minus 1, yeah, so you then split it up here. So sin x plus 1, sin x plus 1 get cancelled, so you have dx minus integration dx by 1 plus sin x, right? 1 plus sin x. But you know, in our trigonometry, we have formula for 1 plus cos x and 1 minus cos x. This is the main reason why I don't want to keep it in the form 1 plus cos x. So I want to take it to, I don't want to keep it in the form 1 plus sin x. I want to take it to cos. So instead of sin x, I'm going to write here cos pi by 2 minus x. That's the only thing. So two main things we have done here. First is this manipulation, and second is instead of sine, I have changed over to cos just to use this trigonometric formula. So now you have the first part is okay. So integration dx minus, now 1 plus cos x is 2 cos square x by 2, right? 1 plus cos x is 2 cos square x by 2. That means pi by 4 minus x by 2. Okay, so that is integration dx minus half integration sec square pi by 4 minus x by 2 dx. Now you can integrate this because you can break sec square into 1 plus tan square, and then you can integrate that. Or you have direct formula for sec square x, so you can do it. Now look at sum number 2. See the difference between 1 and 2. Sum number 2 is sin x by, just the denominator changes to root 1 plus sin x. That's the difference. There's only a root sign in the denominator. So again, if I proceed in the previous method, sin x plus 1 minus 1 by root 1 plus sin x, we end up with, here we are going to split it along this minus sign. So here we will end up with 1 root 1 plus sin x dx minus dx by root 1 plus sin x. So again, by the same logic that I don't want to stay with 1 plus sin x, I want to go to 1 plus cos x so that I can apply the trigonometric formula. So next thing what we do is we change this sign and this sign to cos. So this becomes root over 1 plus cos pi by 2 minus x minus dx by root 1 plus cos pi by 2 minus x. Okay, so this way 1 plus cos x is 2 cos square pi by 4 minus x by 2 dx, and here it is dx by root over 2 cos square pi by 4 minus x by 2. So ultimately it becomes root 2 integration root 2 cos pi by 4 to cos square. So yeah, so this becomes pi by 4 minus x by 2 dx minus 1 by root 2 integration. This is sec, right? Sec pi by 4 minus x by 2 dx. Now you can do this. So this is one category because both the sums they look like same. I mean they are almost similar. That is why we have done this. Okay. Okay. So after this, I want to discuss another different category, say F, which is integrals involving inverse trigonometric functions. Inverse trigonometric functions. So we'll take up the sums one by one, and these are all uh, board sums. Okay. Now, first sum, it is given that minus pi by 2 is less than x less than pi by 2. So this is the sum. Now, I'm going to do this sum by two different methods. So you can then choose your method. Method 1. So in this, different methods means actually different manipulations, nothing else. So what I'm doing here is just like just as we did in the previous sums, we don't want 1 minus sin x and 1 plus sin x. We want 1 minus cos x and 1 plus cos x due to the existing formula in the trigonometry. So we simply change sine to cos. Cos 90 minus theta sin theta. Similarly, right. So now what happens? Just plug in the formula 1 minus cos x and 1 plus cos x. So 1 minus cos x is 2 sine square x by 2. So 2 sine square x by 2 means pi by 4 minus x by 2. And this is 2 cos square pi by 4 minus x by 2 dx. So now this simplifies to tan square. So this is tan. So this becomes integration tan inverse tan pi by 4 minus x by 2 dx. Now, very easily, we write that this is equal to pi by 4 minus x by 2 dx, and then complete the sum, uh, which is, you can do this. So this is pi by 4, integration of dx is x, and then half x squared by 2 plus c. That's okay. But there is a very important point to be noted here, that is, in the entire sum we did not consider this at all. So why has this been given? You have to understand that. Okay. Now since you are dealing with inverse trigonometric function, principal branch is very important. So note that this this step that you have written, you have basically used the property tan inverse of tan x equal to x. But this does not always happen. It happens only if x belongs to the principal branch minus pi by 2 to plus pi by 2, right? So this is the entire thing. So when I wrote tan inverse tan pi by 4 minus x by 2 is equal to pi by 4 minus x by 2, this will happen only if the argument, that is this portion, lies between minus pi by 2 to pi by 2. That is, only if minus pi by 2 is less than pi by 4 minus x by 2 less than pi by 2. So if this thing happens, then only I can write this. So uh, whether this is happening or not, we don't know. We blindly just use the property. So we have to check whether this is happening or not. We have to check this. And how do I do this? This is the way. Okay. Now, what is given? It is given that minus pi by 2 is less than x is less than pi by 2. That means if I multiply throughout with minus sign, then what happens? Pi by 2 greater than minus x greater than minus pi by 2. The signs change multiplying with minus sign. That means, okay, now what I'm doing is dividing throughout with plus 2. So that means pi by 4 greater than minus x by 2 greater than minus pi by 4. Actually, our expression that was given in the sum was x. From there, I am trying to come to the expression pi by 4 minus x by 2. So that is the aim. So first x, I make it minus x, then I make it minus x by 2. Now I will add pi by 4 to get this expression, pi by 4 minus x by 2. Okay. So now let me add pi by 4. So pi by 4 plus pi by 4 greater than pi by 4 minus x by 2 greater than minus pi by 4 plus pi by 4. Okay. So what do we get? If I write it in the opposite order, that is, I'm starting from this portion. So this is 0 less than pi by 4 minus x by 2 less than, this is pi by 2. That means pi by 4 minus x by 2, this expression belongs to the open interval 0 pi by 2. We want our pi by 4 minus x by 2 to be in the interval minus pi by 2 to pi by 2. And we have shown that our expression, that is pi by 4 minus x by 2, that belongs to 0 to pi by 2. But then 0 to pi by 2 is contained within this, right? This is actually a subset of minus pi by 2 to pi by 2. So we got what we wanted. It is within the minus pi by 2 to pi by 2. So that is why this is important. But the thing is, during exam, obviously, we are not going to show this entire calculation. I did this just to explain to you. So what you will do in the exam is this. That is, when you are doing the original sum, when you write this particular step, when you are where you are actually using this property, there you write that uh, minus pi by 2 less than x less than pi by 2 implies pi by 4 minus x by 2 belongs to minus pi by 2 pi by 2. So you don't have to show the derivation, just show that it belongs to, just mention that you have taken care of the fact that we are dealing with the principal branch only while using this property. That's all. Okay, so this was method 1. Now let me go to method 2. Okay, method 2. So our I was tan inverse 1 minus sin x by 1 plus sin x dx. So in the previous method, we directly changed the sign to cos. Here, we will just multiply, just like you rationalize the thing. That is how we are going to do it. That is this portion under the root. We are going to multiply numerator and denominator with 1 minus sin x. So then that will give me, here you will get 1 minus sin x, removing the square root sign. And here a plus b into a minus b will give you 1 minus sin square x, which is cos square x, and removing the square root you have only cos x dx. Okay, so here what we are doing is multiplying numerator and denominator with 1 minus sin x. That is what we are doing. Okay, so now tan inverse. So now you have 1 minus sin x. Again, we apply the old method. That is, we want to go to cos. So we write 1 minus cos pi by 2 minus x by cos. Now here, first let me keep it cos x. No need to change now, right now. You can do it in the exam later, but let me show you why I have to change this cos also. Okay, for the time being, the motivation of changing 1 minus sin x is to apply the formula 1 minus cos x. So when I apply that formula, then this becomes 1 minus cos x is 2 sin square x by 2. So pi by 4 minus x by 2. Now, if I don't change this, then I come to a dead end here. Dead end here, right here. Whereas, if you change this, in this very step, if you change this to sine pi by 2 minus x, then what will happen is, then you apply the formula sin x equal to 2 sine x by 2 cos x by 2. So if you change it, then it becomes 2 sine pi by 4 minus x by 2 cos pi by 4 minus x by 2. So you see the advantage. Why I have to change the cos x also? Because then so many terms will get cancelled. This and one of this will get cancelled. So you will be left with tan inverse tan pi by 4 minus x by 2 dx. So that is equal to pi by 4 minus x by 2 dx. Again, mention the condition that I expressed earlier. Okay. Now here, one thing you should note that uh, that is this step. I mean, from here to here, you don't have to mention this in the exam, but you must note it. From this step to this step. So, important thing to note is when you multiply the numerator with 1 minus sin x, you got root over 1 minus sine x whole square, right? Now, this could be written as either 1 minus sine x, which we have done, or it could have been written as sine x minus 1 also, right? Because 1 minus sine x whole square and sine x minus 1 whole square are same. But why didn't we write this and we wrote this? That's because in you are dealing with your x in minus pi by 2 to pi by 2, or rather independently, or rather independently, we know that sine x is always less or equal to 1. So either sine x is less than or equal to 1. So we do not take this. So here it is sine x minus 1. Now that means your this thing becomes negative. Sin x is less than 1, it becomes negative, and you cannot have a negative sign under the square root. That is why we don't take this. So this is just an explanation. You don't have to write this in the exam. Just keep it in mind that I will express it as 1 minus sin x. That's all. Okay. Now, this same sum I'm going to do by a third method. Method 3. I think initially I told you two methods, but I'm going to do another method, method 3. The sole aim of discussing the same sum with three methods is just that I want to teach you the techniques of manipulation so that you can apply them in other sums also. Now, what's the method 3? It is integration tan inverse. It was root over 1 minus sin x by 1 plus sin x dx. So, you know that 1 minus sin x can be written as sin square x by 2 plus cos square x by 2 minus 2 sin x by 2 cos x by 2, and that means this can be written as either sin x by 2 minus cos x by 2 whole square, or cos x by 2 minus sin x by 2 whole square. Now, which one am I going to write? Right now, I'm taking this. Why I'm taking this and not this, I will explain. So, this becomes ultimately cos x by 2 minus sin x by 2 if you remove the square root sign. And similarly, by following similar method, you get cos x by 2 plus sin x by 2 dx. Now you divide numerator and denominator by cos x by 2. So what do you get? Tan inverse 1 minus tan x by 2 by 1 plus tan x by 2 dx. I don't think I need to explain this, that if you replace 1 by tan pi by 4 and then apply tan a minus b formula, then this portion, that is this portion, becomes tan pi by 4 minus x by 2 dx. So that is equal to pi by 4 minus x by 2 dx. Now the question is, why did I use cos x by 2 is minus sin x by 2? That is, why did I take the cos first? Now see, if you follow the graph of cos and sine, your x was given lying between minus pi by 2 to pi by 2. This was my domain of the function. Okay. And x by 2, this is x for minus pi by 2 because it was given in the sum that minus pi by 2 less than x less than pi by 2. But here I am dealing with x by 2. So obviously this implies that x by 2 will lie between minus pi by 4 and plus pi by 4. So suppose this is minus pi by 4 and this is plus pi by 4. Now I'm using two different colors for the two graphs. First, let us draw the sine graph here, that is between minus pi by 4 to plus pi by 4. So you know sine 0, this is 0, sine 0 is 0, sine pi and pi by 2 is 1. So sine 0 to 1. So this is 1. This is a sine curve from here to here, and then from here also if you check it will be like this. So this is 1 minus 1, right? So this is minus 1. And suppose I use blue for the cos 1. Cos 0 is 1 and cos 90 is 0. So it is something like this. And then here we have this. It will be a bit rounded, anyway, doesn't matter. So if we look at, and you know, this is actually this pi by 4, they cross at pi by 4. So this is not, according to the diagram, this is not pi by 4. Rather, by the cross, that is pi by 4. Because there, both the values are 1 by root 2. Fine. Now if we check, see, from minus pi by 4 to plus pi by 4, if you look at this portion, then throughout this portion, you see your blue curve, that is the cos curve, is higher than the sine curve. That means what I want to say is that in minus pi by 4 to plus pi by 4, your cos x is always greater than sine x. And precisely that is the reason why you took cos x by 2 minus sine x by 2, not the other way around. So this is the reason. So, and this is again for you to understand. No need to write it in the board at all. Just remember that you are going to take this one, cos x by 2 minus sin x by 2 whole square, because cos is greater than sine in this domain, that is minus pi by 4 to plus pi by 4.